This is October, November 2023, paper 22. So, in the first part, he says, mention all the qualities that are base quantities. So, charge, no. It actually comes from voltage is equal to work done by charge, or current is equal to charge by time. So, it's not a base quantity. Electric current, yes, this is a base quantity, so we'll underline this. Force is a derived quantity as MA or F into D as work done, something like this. So again, not time is a base quantity. It only has one unit and is used in other units to make other derived units. Then he says there is under certain conditions, there is an equation that looks like this. Now I can remember this is actually UT plus half AT squared. So he says there are two conditions in which this expression is true. What could be those two conditions? Now, we can see that the UT component is missing, which means that if time is not equal to 0, if t is not equal to 0, then this must be true that u is equal to 0. So we can say that the object is at rest initially, or the initial velocity or the initial speed is equal to 0. That renders this value to be 0, leaving behind only this expression. The second answer would be that, which is always true for these equations of motion, that the value of acceleration is going to be constant. So this object is under constant acceleration, or the value of acceleration throughout these equations of motion will not change. This is the next question. He says this is a velocity time graph. Now a few qualities before we move ahead. The gradient of velocity time graph represents acceleration, and the area under the graph represents displacement. Now, more informally, we used to discuss in the classroom that the area under the speed time graph or velocity time graph represents distance, but we have to be specific over here, because if it's velocity, then it will be displacement. If it was speed, then that could have been distance. Okay, so next he says that comment about the acceleration at t8 and t14 in terms of magnitude and direction. So let's go back. So what's happening at t8 and t14? So in terms of the first question, that is the magnitude, we have to predict their values. We understand that the gradient represents the acceleration. So if he's asking me about acceleration, I will be looking at the gradient. So this gradient, visually speaking at least, is this much steep, right? And the second part of the graph is this much steep. I can very well see just by visual inspection that the gradient of the second part, let's say, and the gradient of the first part, they are different. And which one is more steeper? Gradient 2 is steeper. So the gradient 2 is greater than the gradient 1. So what I can say about the acceleration is that the acceleration at t equals to 14 seconds is greater than acceleration at t equals to 8 seconds. You have to mention these timestamps in your statement, otherwise the answer will not be considered correct. The second part is about direction. Now, since acceleration is a vector quantity, positive values would mean that it is still moving in a straight line, either towards the right side or towards the upward side. A negative answer could mean many things. It could mean that it's moving towards the left side downwards, or it is still moving forward but is decelerating, right? But as we can see that the object still has a positive velocity, it's still in the positive region, it's slowing down. If velocity is decreasing, that means the negative value of acceleration means it is slowing down but still moving in the same direction. So simply looking at the value, since the gradient is positive over here, the acceleration will be positive, and the gradient is negative, so the acceleration will be negative, which is deceleration. So in terms of direction, purely direction, we can say that the direction is opposite to, or in comparison with each other, right? So what we can say using the timestamps is that the direction of acceleration at t equals to 14 seconds is opposite to direction of acceleration at t equals to 8 seconds. Then you get the full marks. He says determine the magnitude of acceleration, which is again in reality or in truth, in hindsight, is actually asking you about the gradient. You can use the equations of motion to calculate this, but I find the gradient method to be more accurate and much easier to visualize in comparison to the rest of them. So if the gradient is being asked for the 4, t equals to 4, which means that this is the coordinate that is looking for. Now, if we look closely, we can see that the velocity is actually 0. But is the gradient equal to 0? No, it's not. The line is still steep. So, and also one thing we can recognize that seemingly the line remains straight in the whole section. So it's my choice. I can choose any two coordinates to make this calculation. So I will pick on this coordinate, which is the easiest one available to me. So this is 4, 0. And I will pick the last coordinate again, just based on convenience. Otherwise, I could have chosen this one as well, which is 8, 10. First x-axis and then y-axis. Over here, the coordinate looks something like this. This is actually 12 at this point, and then goes to comma 20. So it's my choice. Okay. All right. But I like to choose the farthest points, as it is one of the rules for P3 as well. So if you remember the same rules across the exam, it helps you to subconsciously make the right choice. So let's write down these coordinates over these examples and mention to the examiner what you're trying to do. So acceleration, mention that acceleration is equal to the gradient of what? Of the velocity time graph. So that way he knows what you're going to do now. So then mention the coordinates that you've selected, 12, 20, and then 4, 0. Also, please be advised that if you're using something from the graph, always draw a dotted line on the coordinates that you're selecting for the examiner's reference, that you picked these coordinates by choice and you didn't ask anyone else about them. Then simply apply the formula y2 minus y1 over x2 minus x1. Write down the formula properly, and then acceleration is equal to 20 minus 0 divided by 12 minus 4. The acceleration comes out as 2.5 meters per second square. So simply 2.5. Then we have the car is at rest at point X. Okay, fine. At time t equals to 0. Determine the magnitude of displacement of the car from X at time t equals to 12 seconds. So he says that at time t equals to 0, let's say time t equals to 0, what is that point? That point is actually at this location, because this is the time axis, right? So the car is at this point. He says it starts its journey from this point, right? And then goes up to 12 seconds, or maintains its motion for 12 seconds in a certain way with a constant acceleration, right? He says find the displacement. So displacement, mention to the examiner what you're going to do. So displacement is equal to the area under the velocity time graph's line or curve, whatever is given, right? So the examiner knows what you're going to do, what technique you're using. Then it's a simple matter of choosing the triangles and then adding them together. Now let's write those triangles over here, and then you can copy them over there. To make some space over here. So this triangle looks like that there is a base of 4 seconds and there is a height of 10, right? So it's your choice. You can use 1 over 2 into base that is 4 into height that is 10. Now you know that this area is in the negative side, right? So at the time of addition, you can add a negative sign. But if you want to get technical, then you can remove the negative sign and add it with the velocity and still consider this to be addition. This negative will automatically be compensated on the outside when you perform the algebra. The second stage would be to find out the area under the graph. That is going to be this one. Let's see, it's going to look something like this. 1 over 2 into base is 4 up to 12. That is going to be 8 seconds, right? Or you can directly write down 12 minus 4 into the height of this triangle. It goes up to 20 and starts from 0. So this will be simply 20, right? If you write down the whole equation over here, this is what it's going to look like. So the displacement is going to be 1 over 2 into 12 minus 4 into 20 plus 1 over 2 into base is 4 into minus 10, right? If you calculate the whole of this process, it's going to come down to 60 meters. So the answer is 60 meters. Question number 2 is from Dynamics and Forces. Very easy and straightforward question. He says there is a sphere and a balloon held stationary in air, which means that for the whole system, the weight which is downwards is actually equal to the upthrust, right? and suspended by a balloon. Okay, fine. So the volume of the balloon is this much. The total weight of the balloon, string, and the sphere is 65 newtons. The upthrust acting on the sphere is negligible. So he says that the sphere's upward or the upthrust is non-existent. The only upthrust is coming from the balloon. Calculate the density of the surrounding air. So no problem, since the system is in equilibrium, we can say that the weight of the whole system is being supported by the upthrust alone. Since they are both equal, that's why it's stationary. So mg equals to rho gv. Now we can cancel out the g on both sides, which becomes this much. Or if you go back and not cancel it out, you will realize that mg collectively is given to you as 65. So we can't do that. So 65 equals to rho, which is what we want to find out. So rho into g, which is 9.81, into v, which was given as 7.5. So this is 7.5. When you calculate when you calculate rho, the density of the air, it comes out as 0.883. So up to two significant figures, it will be 0.88. Okay. Moving on to the next question. He said the string breaks, releasing the sphere, which means that the sphere is now going to start moving downwards, right? If I clear this up, the string is no more. The string has been broken down and the sphere starts falling down, and the balloon may start rising up because sphere was the only one holding it back. Anyways, he says magnitude of acceleration for the sphere. Now I understand during the exam pressure, you might feel that he's asking about the acceleration of the balloon while it's moving upwards. But it's not. He's asking you about the sphere. So please keep your eyes open. And for any free-falling object, the acceleration is actually equal to the acceleration of free fall. But since we're dealing with all values to be two significant figures, we're going to round this off, or round this answer off to two significant again. He says, state and explain the variation, if any, in the magnitude of acceleration of the sphere. Again, it's about the sphere, not the balloon, moving before it reaches terminal velocity. Because at terminal velocity, the weight becomes equal to drag. Acceleration is 0, hence it attains terminal velocity. So he's saying what happens before that. So there are two stages at that time. So one thing that you need to recognize is that the speed of the object, or you can say that the drag on the object, is proportional to speed. So you will say that as it starts to fall down, as it falls down, right, its drag increases, right? And if the drag increases, the resultant force decreases, and if the resultant force is decreasing, the acceleration also decreases, right? So the equation is going to look something like this. If this is the sphere, this is the weight of the object, and this is the drag, right? And this is the mass of the sphere itself. What does the equation look like in terms of F equals to ma? So this is weight is the pulling force, minus drag is the stopping force. So this is opened up as F equals to mass. We don't know, and acceleration is what we want to find out, or at least comment about. You see, weight is mg. It does not change throughout the motion. Drag is what's changing. It's increasing with the passage of time as the object starts to move faster and faster, because we understand that the drag is proportional to the value of speed, right? So this whole answer starts decreasing. So the value of F, or the resultant force, decreases. Since F is proportional to A also starts to decrease. Eventually, at the terminal velocity, F is 0. Why? Because weight becomes equal to drag. When they both become equal, so W minus D produces a 0 answer, which is equal to ma, so A becomes 0 as well, right? So this is actually a P1 question, or an MCQ question he's asking you in terms of a P2 question for theoretical answer. He says the sphere has a mass of 4 kg, and calculate the total resistive forces acting on the sphere at the instant when its acceleration is 1.2. So at this point, for example, it's quite possible that there is a weight mg, and there is a resistive force F, let's say drag, and the whole system is moving through air. So using F equals to ma, we can calculate that this is the weight, which will be mg, 4 into 9.81 as given in the question, right, minus the drag forces, the friction forces, equals to ma, which is force, into acceleration of the system, which is 1.9. So because of the weight minus the drag forces, whatever we are left with is producing an acceleration. So this is the thought behind it, right? So when you solve this, what you're going to do in terms of algebra, you're going to bring this over here, and you're going to bring this over there. So F comes out equal to be 31.64 newtons, which is 32 newtons up to two significant figures. Question number 3 says that there is a rod and spring. What he does to the spring, okay, spring has a mass of 7.5 grams. It's for the spring. There is a compression of 2.1, and when you compress it and release it, it unwinds and rises up with a kinetic energy of this much. It jumps, right? He says assume that it obeys Hooke's law because we want to make sure that there is no deformation, and kinetic energy of the spring is equal, which means that we are considering a system that is 100% efficient and there is no loss of energies in anywhere, right? And the air resistance negligible, so all the answers and everything is going to be equal to one another. By using the initial elastic potential energy, calculate the spring constant, no problem. So we have two formulas for elastic potential energy. One of them is E equals to half kx square, and one of them is half fx. So out of these two, I can see that from the first formula, I have a spring constant I can use. And do we have the energy? Yes, we do have the energy. So, and they are both equal. Hence, the kinetic energy was equal to elastic potential energy, which is equal to half kx squared. So this is 0.048 equals to 1 over 2 spring constant. We want to find out x. The compression is given as 2.1. Don't forget to convert this into meters square, and don't forget to take a square. So when you solve all of this, your spring constant comes out to be 217.7, which is going to become 220 newtons per meter. Also, an indication why you need to convert centimeters to meters is look at the final unit, that is in meters or newtons per meter. So calculate the speed of the spring as it leaves the surface. No problem, since we understand that the elastic potential energy is equal to the kinetic energy. So whatever energy is available is 0.048 joules equal to the kinetic energy, which is going to be half mv squared, which is equal to 1 over 2. Again, mass in the question was given in grams. So we have to convert it into kilograms because when you're dealing with joules or any other form of energy, everything is going to be standard. So this is 7.5 divided by 1000 into v squared, because speed is what we want to find out. So making v the subject of the formula eventually leads to the answer of 3.57 meters per second, which will be 3.6 up to two significant figures. Part C says there is a maximum energy attained by the spring in terms of gravitational potential is 0.039, which means that the spring has invested 0.048 joules, but the spring only goes up to a certain height h, where we found its energy to be 0.039, which is plausible, which is understandable, because as it moves up, there could be a friction between the spring and the rod. Although he says that there is no air resistance, but it's possible that there is some air resistance as well in the real life, not over here, but in real life, okay? But there is, of course, some friction between the spring and the rod. So that energy that is missing is actually used while moving upwards against the friction between the spring and the rod. He says calculate due to this movement the increase in height, no problem. So gravitational potential energy is equal to mgh, so this is going to be 0.039. Fairly simple, easy question. 7.5 divided by 1000 into value of g, 9.81, into h is what we want to find. H comes out as, when you calculate this, 0.53. So this is 0.53 meters, 0.53 meters. Part 2, calculate the average frictional force exerted by a rod on the spring as it rises. This is the same thing that I was talking about previously, that you need to understand how much energy you have invested, how much energy you got back in terms of the other form of energy, and how much of it is missing. So it's an accounting problem. Always look at this as an accounting problem. So in terms of accounting, we need to balance the sheets, right? So what are we supposed to do? So what is the energy already given? So energy given by the spring was 0.048 joules. Energy removed or taken back successfully was 0.039 in terms of gravitational potential energy. What is the amount of energy that is missing that we can't account for? So when you take the difference, you realize it's going to come out as 0.09 joules. So 0.09 joules appears to be missing in thin air. So we can say that the work done for the frictional forces, or the energy used by friction forces is 0.09 joules. Now, since we know that work done and energy have the same unit and it's just about of purpose, energy is going to be the currency for the work done, and work done is finally when the machine uses up that currency for the work that you're trying to do. So work done for friction is equal to force of friction multiplied by the distance moved along or during that process. So work done is 0.09. Force is what we want to find out because that's going to be newtons. And distance, how much distance did it move? So we realized that the jump that the spring made previously, 0.53, it was moving upwards for a distance of 0.53 meters while it was skidding along the rod. It was experiencing friction. So for 0.53, it had to do all of this. So it had to tolerate all of this. So friction comes out as 0.0169 newtons, which will be 0.017 newtons, and up to standard form it will be 1, 2, so 1.7 into 10 raised to power minus 2 newtons. Okay, all right. So part D, he says there is a compression X and a height H or H gained by the object due to this. So what's the relationship between them? So we have the gravitational potential energy being equal to the elastic potential energy. So gravitational potential is mgh, elastic potential is half kx square. Okay, all right. So we can very well see that the relationship between h and x can be taken from them. So this is h being proportional to x square. The rest of them can be ignored because they are not being compared. What is being compared is h and x. So we can see that this equation looks familiar and looks like a parabolic equation in which at least the power of x is being squared, right? So we have a standard graph for these equations. If it had been a straight line, it would be a straight line. So this is y equals to x. Because this is a parabolic equation, this has a power of square, it is going to go something like this. So this is y equals to x square, right? So this graph is going to look like this, which is a characteristic graph from mathematics of any graph that is y proportional to x square. Anything on y-axis being proportional to anything on x-axis but with a square. So that is all for this. Okay, question number 4 is from momentum. A ball y moves along the horizontal frictionless surface and collides with the ball z. Fine, illustrated as below. All right, you can pause the video and look at this situation, or if you have the paper printed, you can just pause the video and look at the question. A few observations before we start the question. Ask yourself this question before the collision, that whether the object that is contributing to this whole system's momentum, what type of momentum it has. Since it is a two-dimensional momentum, I can see that it is only bringing in momentum along the x-axis. Does it have a y-axis momentum either upwards or downwards? It doesn't have that component. But when I go to the after collision scenario, I can see that the object y has a momentum upwards and the object z has a momentum downwards. Should they exist? No, they should not. Which means that the momentum of y and the momentum of z along these perpendicular axes either should be equal to each other. If this was 10, this should be minus 10. Or another way of saying this would be that they should be cancelling each other out if I add them together. So if I add y plus z, this one, they should be equal to 0. If you take it over there, this becomes y equals to negative z, which is again intuitive because this is downwards, so downwards values are negative, right? So these are the assumptions, or you can say observations, before starting the question. You have to make them as well when you do this question. Okay, all right. So all the values are given to you in the question. You can read them. Nothing special over here. He's mentioning or stating all the angles and values over here that we've already see on the graph. He says calculate the component of the final momentum of the ball y in the perpendicular direction to PQ. So in terms of PQ reference, what is the perpendicular momentum of the ball y? No problem. We have seen this before. The shortcut of components or vector components goes something like this, that if you want to find out something that is in front of the angle, this will most likely be a sine theta. If you want to find out the component that is along the line or touches the angle, this is most likely going to be cos theta. So using this shortcut, if you want to go into the deeper trigonometric ratios, you can try this and you'll find the same answers. So this is going to go something like this. So mass into velocity, the momentum completely, and then sine of theta, which is 27. Okay, so let me write down these components and all of these equations over here. So this is going to look something like this. So the upwards component is going to be 0.25, which is the mass, into velocity 3.7. Since it's the front component, so this will be multiplied with the sine 27. On the other hand, if I wanted to find out the component of ball Z in the downwards direction, this should be mass of Z, which we don't know right now, velocity of Z, which is 5.5, multiplied by, again, the component is in front of the angle, so this will be a shortcut of cos theta. So this will be cos of 44. On the other hand, if I wanted to find the horizontal components, this is going to go something like this. So this would have been a 0.25 multiplied by 3.7 with a cos of 27. If I were to find out the component for the other one, that would have been like this, as mz multiplied by 5.5 multiplied by cos of 44. Okay, so these are all the components that we're looking for. For this part, I've discussed it already. So this will be simply 0.25 into 3.7 into sine of 27. If you calculate, this is going to come out as 0.42 Newton seconds. This will be 0.42. So considering the component of the final momentum, each ball in the direction perpendicular to PQ, calculate mz. As I've explained before, if you consider the perpendicular components, should they be equal to each other or should they be different? They should be equal to each other. Why? Because before the collision, there was no y-axis momentum. There was no perpendicular momentum. So they both should be equal after the collision. Or they should both cancel each other out because it did not exist into the system before it started. Right? Or you can say it was not invested into the system. It was not brought into the system. So it shouldn't exist. Which means that both perpendicular components should be equal to each other. So let me write this down over here. So one of the components is going to be in the upwards direction, which is 0.25 into 3.7 into sine of 27 being equal to mz multiplied by 5.5 multiplied by sine of 44. Now when you write this equation down, you have already calculated this part in the previous part, 0.42. They should be equal to each other. So this is what it's going to look like. Okay, so 0.42 calculated by this part equals to mz 5.5 into sine of 44. Take this over there, divide it, and you will find mz to be 0.11 kg. So this is actually it's 0.109, which becomes 0.11. We have the third part. During the collision, the average force exerted on y by z is Fy, and exerted on z by y, on z by y, let's say, if it is in this direction, that is Fz, and this will be Fy. Basically an understanding of Newton's third law. So he says magnitudes, what will be the values of the magnitude? They will be equal, but the directions will be opposite. This is what happens in a collision. Now the next part is interesting in terms of one of the unspoken rules of momentum questions is the relative speed rule. And students generally forget about this. This is relative speed rule. This is only applicable when the system is perfectly elastic, the first condition, and you will see that in the question, the masses of the questions or of the values are not given. The masses are not given, right? You will notice in the question the masses are not given, and it mentions or emphasizes that this is a perfectly elastic collision, and then he will ask you about the velocities. So this is an indication that you were supposed to use the relative speed rule. Okay. Now for the relative speed rule, there is a simple method. There is a simple way how to use the values. So if the objects are moving towards each other or the objects are moving away from each other, this means that the objects are moving opposite to each other, which means that their velocities, let this object A and let this be object B, their velocities will be added together, irrespective whether the B is moving in the negative direction or whether A is moving in the negative direction. We're not supposed to include the directions sign. We're supposed to just add them according to this formula. Similarly, if they were moving in the same direction, like this or like this, in this case, if B is leading, or you can say if the velocity of B is greater than the velocity of A, or you can say B is leading, then the velocity of B should be greater than A. Then that would be VB minus VA. They will be subtracted if they're moving in the same direction, right? And in this case, VA should be greater than VB because VA is leading. And we cannot let them collide again, because if they collide again, this will eventually fall in the inelastic collision. In elastic collision, there is only one collision. Generally, this is just a trick. And then it will become VA minus VB. So when they're moving in the same direction, they're supposed to be subtracted, but there is a way for subtraction. Whoever is leading will be considered larger. Whoever is lagging behind will be considered smaller. So according to this idea, let's read the question. He says that this is the before situation. Now, since they're moving away, since they're moving towards each other, so I can write down that this is the collision before and this is going to be the collision after. So before, they're moving towards each other. So I'm going to simply add them together. Notice again, 6 is moving towards the left. I should add a negative sign. But for the relative speed rule, signs will not be considered. Only consider them for addition or subtraction. Are they moving opposite to each other? Yes. So I will add them together. So this will be 4 plus 6 equal to after. What's happening after? It says B moves back original path with a speed of 2 meters per second. Moves back, which means B is going to go back with 2 meters per second. Okay, fine. So it is simply going to be considered as 2 plus VA. We don't know what VA is going to do. Either way is moving along the same direction, either is going to go back. I don't know that. I will know this after solving the equation. Let's see what happens. So this becomes 10 equals to 2 plus VA. VA comes out as 8 meters per second. Is this positive? Yes, it's positive, which means that this was moving towards right side at 8 meters per second, and this was moving towards the right side with 2 meters per second. This is the scenario after it collides. Okay. All right. So according to relative speed rule, this answer is going to be 8.0. Simple as that. Question number 5. He says a beam of vertically, now this is from Malice's law of polarization. You will notice that from the recent past papers, he's giving this question again and again. This is vertically polarized, which means that this is already along the line of this filter. Okay. All right. So this is a transmitted beam. If I wanted to find out the equation, that would go something like this. This is going to be I naught, and this is going to be the I. And the equation of Malice's law is I equals to I naught cos square theta. Okay. All right. He says that the filter is then rotated through an angle of 360 degrees, which means that this filter will be rotated through 360 degrees, and draw the response what you're going to get. First and foremost, do this one exercise that predict what's going to happen at the special angles. For example, when it was at 90, then rotated enough when it was at 180, then rotated enough at 270, then rotated enough back to 360. What's going to happen at these four locations? So at the very beginning, at 0, when there is no angle, the filter is along the line, because 360 and 0 degrees are exactly the same point. So it will have the maximum value. But at 90, I can see that the plane becomes horizontal, and the wave itself is still vertically polarized. It will not be able to exit. So at 90, I should get 0 intensity. Then back to 180, it comes down again, which is again going to open up the aperture for the vertically plane polarized. So this 180 is going to produce a maximum wavelength. Then at 270, again, let's go back to 270. At 270, the filter is again, this one has rotated up to 270. The filter is like this. The wave is like this. Will it be able to pass through it? No, it will not be able to pass through it. So this will be 270. Again, back to 360 or the starting point, the aperture aligns with the direction of the wave. So this becomes like this. So the graph is going to look something like this. Also notice that there is a cos square function. Now, since you're dealing with light, right? If it had a cos function, a cos theta, then it would go something like this, right? Like a sinusoidal wave. But since this is a cos square wave or cos squared, the whole graph is going to produce a positive value. It will never go into the negative. So this graph looks something like this. Okay. All right. Now let me show you a visualization. What's going to happen at these locations? What's happening at these points? Okay. All right. So let's go towards this diagram, you can see that for the sake of understanding at least, or for the sake of decision, this is my I naught. This is the original beam. And this will be my I, or the output beam, which is going to be equal to I naught cos square of theta. Okay. And this location is our filter. No problem. So let's see that right now at this location, I can see that my filter is allowing the wave to pass through it. Okay, I can see that the wave can pass freely. If I change its aperture to 90 degrees, you see at this point, at this location, we can see very clearly that, let's say this is my starting point. Let's say this is my 0 degrees, right? The whole wave is allowed to pass through. Now, when I shift this to 90, you can see the output wave has completely vanished, right? So at this point, we are standing at 90 degrees and the output has become 0. It has completely vanished. Similarly, if I, just a moment. So if I allow this to move even further to 180 again, so at this point, the angle is 180 degrees and I get the complete wave output back as well. So I would advise you to visualize it like this, that if we move it again up to 270, it vanishes completely. Then back to 360, it starts to emerge again, right? So I hope that we understand how this functions or how this works. Okay, all right. Coming back to the lesson, so this is how it goes. This is what the aperture was like. This is what the filter was being visualized in the animation. Okay, so now he gives you that the initial incident beam is this much, the filtered beam is this much, calculate the angle theta. Very straightforward question. So I equals to I naught, always mention the formula. So this is 4.2. The intensity initial is 7.6. Cos square of theta we don't know. And one mathematical mistake that you will do over here is that, for God's sake, please first take this over there, divide this, whatever answer you may get, whatever answer that may be. Okay, so let me solve it for you. Okay, so 4.2 divided by 7.6 gives you an answer of 0.55. So this is 0.552 equals to cos square of theta. This is still a square. So please don't forget to take the under root. So first take the under root here and then take the under root here. This becomes under root of 0.7433. So this is 0.7433 equals to cos of theta. Now take the cos inverse over there. So theta is equal to cos inverse of 0.7433. So shift cos inverse of that answer is going to come out as theta equals to 41.97 degrees, which is going to become 42 degrees up to two significant figures. Again, a repeated question. He says, what's meant by diffraction? You can simply write down that diffraction was basically when a wave passes through a narrow gap, the vertical wavefronts or parallel wavefronts become circular. So how to write this down as a typical standard answer for marking scheme or for the examiner, that wave spreads out into geometrical shapes while passing through a narrow gap, right? You get your 2 marks. Next, part C, he says it's a diffraction grating question. So this formula should be n lambda equals to d sine theta. So I remember the formula. Okay, fine. Let's move ahead. He says that we have a third order. Wavelength is mentioned. Angles are mentioned. Order is mentioned. Very straightforward question. He says find the d. So n lambda equals to d sine theta. So n is 3. The order of diffraction, what's the wavelength? 4.3 power 7. So 4.3 into 10 raised to the power minus 7 equals to d is what we want to find out, and sine theta is 68 degrees. Also remember that in these questions, sometimes what the examiner tries to trick you into is that he will mention that this whole angle is 120 degrees. What will you do then? You'll have to divide this into two parts. So you only consider the angle of one single side. So luckily over here, he's already mentioned the angle for one side, but sometimes he does not do that. So D in these calculations comes out as, please perform the algebra correctly. The D over here will come out as 1.39 into 10 raised to the power minus 6, which will become 1.4 into 10 raised to the power minus 6. Then we have determined a different wavelength of visible light that also produces. Now, this is a tricky question, right? So it will take a bit of understanding or a bit of, back and forth, argue with yourself and discuss how it's going to go. So he says the setup is same, everything is same, the angle is also same. We want to produce the same pattern or a same maximum, diffraction maximum at an angle of 68 degrees. But the light should be from the visible spectrum. So is there a wavelength variable in the equation? So n lambda equals to d sine theta. Yes, there is a lambda available in the question. So if the crystal has not changed, then the d has not changed. The line spacing is same. If the angle is exactly the same, then the sine theta is not changed. So one scenario or old situation being compared with a new situation with a new lambda can be equated together because their d sine theta will be same for both situations, right? I'm subjecting a new wavelength into the same situation, but I want a wavelength that does this for me. So how can we solve this? So first, remember that the wavelengths of visible light actually starts from 400 nanometers and goes up to 700 nanometers, 700 being red and 400 being violet, indigo, purple, whatever color you choose to label that with. Okay, so going back, this is actually 430 nanometers. So it's already violet. It's already purple color. So 430 exists on the spectrum somewhere along this line. This is 430. So I can go up to 700 and still be in the visible spectrum and try to do that. Okay, so in the old scenario, we had a 3 order at a wavelength of 430 nanometers. This was 430, right? Yeah, so that's 430. Okay. What can I do to, okay, so I can't go back. I can't reduce more than 400 because if I do so, I will exit the spectrum of visible light and I will enter into ultraviolet, right? So I have to go somewhere on the larger side. So in terms of n and lambda, what should I do? Logically speaking, what should I do? So I am looking for a larger wavelength, right, which is greater than 430, but preferably less than 700. Since this is a hater trial method, but we're doing this logically, I can see that if I want to increase lambda, I should decrease n because I want to keep d sine theta for both sides constant. If this n was higher and lambda was smaller, this lambda is supposed to be larger, then n is supposed to be smaller. So they both come equal to d sine theta. That's how they're related, right? So the next integer I can try for n by reducing 3 to 2. So instead of 3, I will write down, or I will try 2 or the second order for another wavelength, which I'm trying to find out. It's a hit and trial method and see what happens. So this is 430 nanometers again with 3. So lambda comes out as 645 nanometers. Is this wavelength within this range? Yes, it is. It's less than 700. So it is within the visible spectrum range. So this is my final answer. This is going to come out as 650 nanometers, which is a very orange red shade color. Okay, so that is how we have tried to solve this question. I understand there is no direct method to this. You'll have to argue. You have to argue with this equation or try to be reasonable with this, right? Question number 6. He says a metal wire has a resistance of this much. Okay, fine. This is okay. Notice this is resistance per unit length. So this is actually R divided by L. The wire has uniform cross-sectional area of this much. Okay, thank you. So resistivity of the metal, no problem. So we have a formula for resistance equals to rho L over A. Now, how should I put in the values? I'm supposed to find out the resistivity. I have the cross-sectional area, but I don't have the R and L. But do I have them in a different format? Yes, it's an R over L format. So let's bring L over there. This becomes R over L equals to rho over area. And then take A over there. So this becomes rho equals to R divided by L multiplied by cross-sectional area A. Do we have their values individually? So this is R over L given to me as 0.92. As represented by the symbol as well, or the unit as well. So cross-sectional area is also given to me over here. So this is rho equals to simply 0.92 multiplied by 5.3 into 10 to the power minus 7 Rho comes out as 4.876. This will be 4.876. So this is going to be with the power of minus 7. So this will be 4.9 into 10 raised to the power minus 7. Right? Next question, a battery of EMF E, negligible internal resistance. Okay, thank you. So LDR is given to us. This is the LDR. And this is a fixed resistor. There is a voltmeter connected to the LDR. Okay, so to remove any confusions over here, you could have visualized it this way, that the voltmeter is not connected over here. Rather, the voltmeter is actually connected something like this. Then it makes it more easy to visualize. This is how the voltmeter is actually connected. So if you extend those wires by removing them from here and connect them over there, it nearly makes no difference. There is no difference to that, right? So if you do that, this is what you get. So let me remove those lines again to make it simple for you to understand that what he was trying to do. He was just trying to confuse you. So the voltmeter effectively is only measuring the voltage of the LDR. Okay. All right. So the resistance of the fixed resistor is 1400. The LDR is 1600. Okay, fine. He says that the voltage reads 6.4. So the voltmeter is reading 6.4 volts. No issues at all. So show that the reading of the LDR, show that the current in the LDR is this much. No problem. Do we have its resistance? Yes. Do we have the voltage? Yes. So simply using Ohm's law, the LDR is consuming 6.4 volts, and for that it is causing what amount of current? I don't know. Its own resistance 1600, and the current comes out as 4 into 10 raised to the minus 3 amperes. So we have this under record? Yes. We have successfully shown what we get. Okay, so moving on, he says calculate the number of free electrons passing through the LDR in 3.2 minutes. This is a trick question because you generally forget this equation that I is equal to NAQV, right? And you generally also forget this equation that I equals to Q by T. And Q can be replaced by number of electrons divided by T. And this E is actually the elementary charge, which is 1.6 power minus 19. These two formulas is what you generally forget. So no problem. Do we have the current? Yes. Do we have the time? Yes. That is 3.2 minutes. So in place of current, I'm replacing the previous value, which is 4 into 10 raised to the power minus 3. Right? And the number of electron is N. The elementary charge is 1.6 power minus 19. Divide by time, that's 3.2 minutes. So that has to be converted into seconds. So 3.2 multiplied by 60. So when you take this over there, multiply, and then bring that over there to divide, this N comes out as 4.8 into 10 raised to the power 18 electrons. So this process actually allowed this many number of electrons to pass through within a time of 3.2 minutes. He says calculate the EMF of the system. Very, very simple and straightforward question, but let's say for the sake of example, you are unable to understand this. There are many methods to do this, or there are many methods to go about this. No need to worry about them. We're going to try all of them. So first method, which is very simple, is actually a potential divider rule. This is a PD divider rule. That if you want to find the EMF or the voltage of any resistor in a series combination, divide its resistance with the total resistance and multiply it with this battery EMF. Now we understand that this battery EMF or a portion of that battery EMF goes to the LDR as 6.4 and some of it goes to the 1400. Do we know the voltage of the 1400? No, we don't. No problem, but we know its resistance. That's good enough. So I'm changing the formula and I'm writing this down as this. So this is 1600 divided by 1600 plus 1400. Why am I adding them together? Because for the total resistance to be calculated for a series circuit, they have to be added together. Simple. And multiply this with the EMF of the battery, which was being shared between them. Do I know this value? No. This is what we want to find out. But do I know the voltage I'm going to get? After solving this equation, I should get the voltage of the 1600. Do I have that? Yes, that was 16.4, right? So after calculating this, take this over there, then divide this over there, and then EMF, the value of EMF comes out as simply 12 volts. Very simple and straightforward question. The other method to do this would have been, or would have gone something like this, that you simply used V equals to IR. If the current through this LDR is this much, as mentioned in the circuit, the 1400 would be getting the same amount of current. So apply V equals to IR over here again. You will get the voltage of this fixed resistor. Now this voltage added with this voltage will be the voltage of the battery. Again, that's another method. So this would be going to go something like this. So this is 4 into 10 raised to the power minus 3 into 1400, whatever answer voltage this may be. Add this with 6.4, you will get 12 volts again, right? Another method of this would be which is you can say a variation of the voltage divider rule, goes something like this. It's written in the syllabus as well. But the formula suggests that V1 divided by R1 is equal to V2 divided by R2. Okay, or the ratio of voltages is actually equal to the ratio of resistances. You have the voltage of the LDR, you have LDR's resistance, you have the fixed resistor resistance. You could have found out the voltage of the second resistor by this method again, which would be this answer that you got by using V is equal to IR. Once you have this voltage again, then it would be follow the same process by adding the voltages of both components, which would still be equal to the voltage of the battery. So not one, but there are three methods to solve this. But I like this one because this reminds us about the voltage divider being able to solve or being able to divide the voltage between two resistors in a series combination. Now this next part also has many methods. It says determine the ratio of the power dissipated in LDR and power of the fixed resistor. First, remind yourself about the formulas of power. So this is I square R, we have IV, and then we have V square over R. I find that the easiest one would have been I square R or simply IV. Or we can try all of these methods and you will see that every single one of them gives you the same answer. So let's try the I square R method first. So the power of LDR would be I square R, which is 1600 of LDR, divided by I square into 1400. Now, do I need to worry about the current? No, they're in series. So I square is going to get cancelled out. So it's simply 16 by 1400 gives you an answer of 8 by 7, which comes out to be 1.14. Let's try the second method, which is IV. So IV divided by IV. Do I need to worry about the current? No, because current is same, gets cancelled out. So the voltage of LDR was 6.4. The voltage of the other component or the fixed resistor would be simply now 12 minus 6.4 if you've previously calculated the EMF, which was 12 volts, right? So when you put that over here, let's try that. So 12 minus 6.4 gives me 5.6. When you calculate 6.4 divided by 5.6, we get 8 by 7 again, which is 1.14. For the first time, I'm writing the fraction just to show you guys that I'm getting 1.14 from the same fraction. Don't think that 1.1 is an answer from a different equation, right? That's why I'm writing the fraction, otherwise it's not necessary. Now, the third method would be V square over R. So V square over R divided by V square over R. This will be 6.4 square divided by 1600 divided by 5.6 square divided by 1400. Now, when you try this again, guess what? You get 8 by 7, which is 1.14. So to two significant figures, this is going to become 1.1. So you choose any method that you like. You choose any formula that you like and go ahead with this. You will get the same answer. But be advised that you should be dividing power with power. These three formulas what? For power. C part. He says that the environment conditions are changing, causing the resistance of LDR. So the resistance of LDR is decreasing. So it is inversely proportional to light intensity. So if it is decreasing, light is increasing. That's the preemptive assumption before moving on. He says state whether decrease, increase, or no change is going to occur in three places. No problem. The intensity, yes, we figured it out. So intensity is increasing. It's a sunny day, that's why resistance is decreasing now. The current in the battery, what's going to happen? If the resistance of the LDR decreases, we can see very well from the system and the circuit, it's a series circuit, right? So for the current equals to E divided by resistance of LDR plus the resistance of the fixed resistor. If you decrease this value, the whole value decreases. And if you notice that it is inversely proportional because EMF is not changing. So if you decrease the resistance, the current increases. Simple. Right? So this will also be an increase in the value of overall current. The reading of the voltmeter. This is a bit tricky, but don't worry about it. You see, if the resistance of this LDR decreases, according to the voltage divider rule, it will go something like this, that this is 1600 divided by 1600 plus 1400 multiplied by the EMF of the battery, which is 12. Now, if you replace this with a smaller value, let's say, if you decrease this value, this is the voltage of the LDR, the potential divider rule. If you decrease the value of the LDR's resistance, the voltage of the LDR also reduces. Because if this resistance is decreasing, then the EMF's larger share will go to 1400 and a smaller share will go to 1600. You can try this question on your own by making a new question. You see, the battery is 12 volts as it is. You have a 1600 ohm resistor, right? And you have a 1400 ohm resistor. Now, if the resistance is decreasing because of the light, take a hypothetical value yourself. Let's make it 800. Apply the voltage divider rule, you will see that the voltage is decreasing. Now, since the voltmeter is only connected along the LDR, the voltage reading will decrease. Okay, all right. Question number 7 is from radioactivity, and primarily this is, the whole question is about memory. So underline all the particles that are fundamental. They are not fundamental. So antineutrino is a fundamental particle, so we can't underline this. A boron is a family that has protons and neutrons, right? So this is not a fundamental, so this will be underlined. Nucleon, again, is not a fundamental that contains protons and neutrons. And positron is a fundamental that belongs to leptons, right? It's a fundamental family. So part B, he says a nucleon of thorium or nucleus of thorium 23090 decays by emitting a few stages of alpha and beta to go back to lead 20682. Determine the total number of alpha and beta particles to do this. Now, first things first. First, visualize that alpha is 42 and beta is 0 minus 1. So which one of them I can use to figure out how many alphas would have been used? You see, beta, the mass number or the atomic number does not change, but the mass number of alpha is 4. So I will use alpha to check out how many alphas have I removed, because beta would not have determined or would not have changed the upper value, okay, in layman's terms. So I am changing the upper value from 230 to 206. So the difference between them is 230 minus 206 comes out as 24. Now, if I'm causing only alpha emission, then divided by 4 gives me 6 alpha particles. So 6 alpha particles must have been released. If that's the case, then what's happening with the proton number? So let's start with that. So 230 of thorium, let's say, at 90 emits 6 alpha particles with 4-2. Then what are we left with? So the upper number has already been calculated as 206. But what about the lower number? So 6 multiplied by 2 is actually 12. So 90 minus 12 gives me an answer of 78. Now, what answer do we have? We have an 82 on the lower side. It's not 78. So how do I make 78 into 82, which is the lower number? So I'll have to add 4. Now, how do I do that? We do this by the addition of beta, because we understand that when beta emission takes place, one number increases. So let's say if I was dealing with uranium-235-92, something new would be formed, or uranium again will be formed as 239, or something else will be formed. Sorry, for example, X will be formed at 235 plus 93 with beta 0 minus 1. Because charges have to be conserved, nucleon number has to be conserved, 93 plus minus 1 will give you 92 again. So this means that because of beta, one number in the lower part, or the proton number, increases by 1. So if I want to increase the proton number from 78 to 82, finally, I'll have to add 4. And only one way to add in 4 is to introduce a beta negative with the same amount. So there should be 4 betas and 6 alphas that are going to do this. So 6 alpha and 4 betas. Okay, all right. Next question is, he says that there is a meson charge of -1. Mesons are those particles that have a quark and an antiquark. So he says the quark composition of meson includes charm antiquark. Now, the charge on the charm quark, as in this table, is +2/3. Right? So he says it's a charm antiquark. So means that it will be a negative 2/3e plus something x equals to the overall charge of -1e. So you take this over there, this becomes x naught equals to, or the unknown charge equal to -1/3e. Right? So who has -1/3e? So -1/3e belongs to these 3 people. So it could be down, strange, or bottom. He's saying what type of quark this may be. So it could be down, it could be strange, it could be a bottom charge. All right.